Great. So hello again, everybody, and welcome to anyone who didn't make it along on Tuesday. So this afternoon, we're going to get into syntax of OpenMP. I'll start off looking at parallel regions, and then in the second section, we'll look at work sharing directives, which is essentially how OpenMP deals with parallel loops and one or two other cases. So as last time, please feel free to ask questions via the chat facility, which you get to by opening the tab down at the very bottom right of the window, the pink arrows, and then clicking on the speech bubble. I'll stop at various points and invite questions, but please feel free just to type away as we go along. Good, so let's get ourselves into some syntax here. So the parallel region directive. So remember that the code within a parallel region is going to be executed by all the threads. In Fortran, this looks like !OMP parallel, then the block of code, and then the end parallel directive. In C and C++, it's #pragma OMP parallel, and then a block of code in curly braces. So actually, technically, in C and C++, what follows the parallel directive is actually a C or C++ structured block. So as well as a block of code in curly braces, a single statement is also allowed. But I recommend that you don't code like that. It's very easy to write a parallel region with a single statement and then go back and decide that you want another line of code and forget to add the curly braces. And it can take you quite a while to figure out what on earth's going on. So I recommend, even if the block of code is only a single line, it's helpful to use the curly braces. So something else to note is that the curly brace at the beginning here cannot appear on the end of the directive. So that's kind of normal coding style with things like for loops and if blocks and so on, is to put the curly brace at the end of the first part. But that doesn't work with OpenMP directives. And the reason for that is that the code must be able to parse correctly without the OpenMP directive there. So the curly braces the first opening curly brace needs to come on the next line. So just a very simple example to illustrate how this works again. So here's my code. So I have a call to a function called Fred, and then a parallel region which contains a call to a function called Billy, and then after the parallel region there's a call to Detsy. So what's going to happen here is that the master thread that starts executing at the beginning of the program executes Fred. Start of the parallel region, then say, at least logically, though as we discussed last time, the implementation may have already really created the threads. Then a team of threads is created or at least activated at this point. So I've shown a total of 4 threads here. So that's the master thread plus 3 others. All 4 threads execute Billy. At the end of the parallel region, the master thread waits for all the other 3 threads to finish executing Billy and get to the end of the parallel region. And once that's happened, the master thread then carries on executing back in the sequential part of the program and executes Daisy on its own. So if we just want to program with parallel regions and nothing else and no other features of OpenMP, then in order to do anything useful, we need a couple of function calls. So the first one of these is to find out the number of threads being used. So this also serves to introduce the runtime library functions. So in Fortran, we get access to these from the OMP_lib module. So you need use OMP lib, so that's a standard name. And then the function is OMP_get_num threads. C and C++, the function prototypes come from the omp.h header file. Again, that's a standard name across all compilers. And again, so OMP_get_num_threads returns the value. And what this is really returning is the number of threads currently executing this parallel region. So what happens if you call this from outside a parallel region? And the answer is it'll return 1. So really the meaning of this call is how many threads are there currently executing. So just to be careful, if you want to, for example, if you want to print out the number of threads that are executing your OpenMP program, you have to call this inside a parallel region to get a meaningful answer. And the other thing we'll need to do anything useful is to find out the number of the executing thread. This is OMP get thread num. So that's I think it's a slightly poor choice of naming convention. So I think OMP get num threads and OMP get thread num are a bit too similar. So just be careful that you're typing the right one in the right place, in the right context. So thread numbers start from 0 and go up to 1 less than the number of threads in the team that's executing the parallel region. So 1 less than what OMP get num threads will return. Any questions so far? Okay, good. So we can also specify some additional information for the parallel region directive through what are called clauses. So these are just extra pieces of syntax that appear on the end of the parallel directive. And these can either be comma or space separated. In particular, one of the things we do with these clauses is to control shared and private variables. So inside a parallel region, variables can either be shared, where all threads see the same copy, or private, where every thread has its own copy. And this behavior is controlled by the shared, private, and default clauses. So the languages are pretty similar. We have a shared directive and then a list of variables, a separated list of variables in brackets, and same for private. And then we can also specify the default behavior for variables which are not in one of these lists. And that default behavior in Fortran can either be shared or private or none. The slight weirdness that in C and C++ you're not allowed to have default private. It can only be shared or none. So I'll talk about what none does in a minute. So for shared variables, then nothing new is created. Every thread inside the parallel region just refers to the existing storage location that the master thread already had access to before the parallel region starts. For private variables, every thread gets a new copy on entry to the parallel region, and these are uninitialized copies. We can also declare variables inside the scope of a parallel region, and in which case those are automatically private, and you cannot specify those in the private clause because anything in the private clause must currently be in scope. So if the scope of the variable is inside the parallel region, you don't put it in the private clause, the compiler will complain it's automatically privatized. And those private copies are completely separate storage from the variable that already had that name in the master thread. And that original copy is unaffected by any changes to the private copies. So that the original copy in the master thread persists. So it's still there after the end of the parallel region, and it's unaffected by any changes that were made to the private copies. In C++, this all works with objects. So you can have objects in shared and private clause. Private objects are created by calling the default constructor. I already mentioned the default clause, and this is probably the single worst design decision in OpenMP. So, if I was asked, say, with hindsight, what would be the one thing that you would go back and fix in OpenMP and do differently, and it would be this. The reason is that if you do not specify a default clause, that's the same as specifying default shared. So any variable which doesn't appear in one of the lists will be shared by default. And that turns out to be really, really dangerous. It's very easy to miss a variable out, and it gets shared by default, and then is prone to race conditions. So my strong recommendation to you is, even though it involves some extra typing, is always use default none. Okay. So for Fortran programmers, it's a bit like nobody learned the lessons from implicit none. So it's a bit like saying, always a good idea not to rely on the default typing. So use default none. Then if you miss some variables out, the compilation will fail, and most compilers, in fact, all the compilers I know of, will give you sensible error messages. It will tell you that it was expecting, give you the name of the variable and tell you that it was expecting it to be declared in one of these lists somewhere. So Kevin asks, is there any way to pass an obscene number of variables to the clauses without typing each one out? And the answer is no. But if you're in that situation, there are other defensive mechanisms you can use. So I will talk about this later on in the course, but just as a quick preview, if you're in that situation, then you probably have a pretty terrible piece of code, and it's worth doing something to refactor it. Tends to be a problem in Fortran, and the way to deal with that is essentially to refactor your code and extract the code in the body of the parallel region into a separate routine. And then you can make everything that you would like to be private can be local to that routine. We'll come and talk more about that in detail, that'll make more sense later on. Okay. And in C or C++, you can get rid of a lot of the private declarations by declaring variables inside the scope of the parallel region. But otherwise, yes, it's a bit of a problem. But if you do have a lot of variables in your parallel region, then you really, really have to be careful to think about what's the correct behavior for all of them. And that can be, especially some old inherited code, that can be pretty nasty. Here, okay, so we don't have very much syntax yet, but so this is a little bit contrived. Okay, I suppose I have a shared array, and I want each thread to initialize a different part of it, to write some values into a different part of the array. Okay. So here's my array A here. So I've chosen some fixed dimensions, and suppose I want to use 4 threads, and I want each thread to initialize a different row or column depending on how you like to look at it. So I've got it as columns here. So a different column of this array. So thread 0, going to write the blue column, thread 1 the red column, and so on. So Tom asks, is there any reason why my ID isn't declared in the scope of the parallel region here? No good reason. That's a perfectly good solution. I just wanted to illustrate the use of the private clause here. So declaring int my ID here is a perfectly good solution, and the same for the loop iterator as well. No problem. So in general, that's a good idea. Sometimes just the way code gets written can be a real pain to refactor everything like that. But in general, it's a good strategy in C and C++ to declare private variables inside the scope of the parallel region. It reduces the amount of work and thinking that you need to do. Here's my parallel region, and so each thread reads its own thread number, and then loops over the elements of the column of the array, writing some values into it. So I take my own advice. I write default none here, and so then I have to specify what do I want as private. Well, for sure, my thread ID needs to be stored privately. Every thread wants a different copy of that, and similarly for the loop index as well. Every thread needs its own copy of the loop index. Then the array A can be shared. It's okay, there's no race condition because different threads are writing to different parts of it. And then the final variable I have here is n, which is the extent of the loop here. And it's fine to make that shared. So because that's a read-only variable in this context. Okay, so no problem having shared. So Nicola says, as far as he remembers, C, C++ and Fortran work on row-wise and column-wise respectively. Okay, will the way I parse the arrays affect the performance? So the answer is yes. Okay, so I tend to steer away from this idea of rows and columns in C and C++ and Fortran, because that kind of assumes that you're dealing with two-dimensional arrays that represent a matrix somehow. So I find it more sensible to think about the memory ordering of indices. Okay. So in C, the rightmost index varies most quickly in memory. So the rightmost index in an array is contiguous in memory. And yes, there are implications from cache behavior to do with which way round you would want to do this. Okay. So this is the right way round for performance. You want each thread accessing a contiguous part of the address space. Yep. So in answer to Tom, okay. So here's the alternative. So is to use the C language scoping rules and declare my ID and I inside the parallel region. As I said, generally would prefer this tactic. It's not always feasible or convenient, but most of the time that's a good idea. Okay, and so for the Fortran version, so I haven't showed the declarations here, but it's exactly the same idea. Okay, except now the array indices are the other way around. So leftmost varies most rapidly in Fortran. So again, I have this is the right way around for performance reasons. A couple of other things to note about Fortran. So just be careful. Thread IDs start from 0 and array indices start from 1 by default. So that's a possible source of bugs. So get around it by adding 1 here, for example, or declaring your arrays to start at 0. Either will do the trick. In Fortran, the loop index here will be private by default, because loop indices are special things in Fortran, whereas they're not in C and C++. In C and C++, they're just regular old variables. In Fortran, they are special objects in terms of the actual the underlying language, and so the compiler knows to make these private by default. You can still declare it here. The compiler won't complain, but even with default none specified, if I omitted I from the private list, that would be fine. Okay, so any more questions before we move on? Okay, so if you do end up with these long lists of variables, then you can end up with rather long directives, and it's convenient to split directives across multiple lines. So this is just the syntactic trivia of how to do that. In Fortran, it depends whether you're working with fixed source form or free source form. Fixed source form, what you do is you put an ampersand on the next sentinel, exclamation mark $OMP, sentinel, remember, put an ampersand on the next sentinel, and then carry on the next line. In free source format, the ampersand goes on the end of the first line, but you still need sentinel here. In C and C++, it's the usual way for splitting preprocessor pragmas. Use a backslash and then continue directly on the next line. The only gotcha here is that you cannot have any white space after the backslash. And if you do, you typically end up with some really bizarre compiler errors, because what will happen is the compiler will try to compile the rest of the directive as a line of C, and you can just get some really weird compiler errors from that. Okay, so as well as shared and private, we do actually have a couple of other alternatives. And one of these lets us initialize private variables. So private variables are by default uninitialized at the start of the parallel region. If we want to initialize them, then we use the first private clause instead of private. And what happens here is that the private copies are created on every thread and then initialized with the value that the original variable had when the master thread entered the start of the parallel region. However, it's worth noting that use cases that tend to be fairly uncommon. Very seldom really need to do this. And it's occasionally works out as a performance optimization, but most of the time you should just think twice. If you feel yourself wanting to use first private, then just step back and say, do I really need that? And it's possibly tempting to use this for read-only variables, but shared is almost always perfectly okay in that circumstance. And by using first private instead, all you're doing is creating unnecessary copies and incurring some cost of making the copies. For scalar variables, it's probably negligible. But if you start having significantly sized arrays and declare them first private instead of shared, then there can be quite a significant cost in initializing those. Again, this works for C++ objects. The default copy constructor will be called to create and initialize the new object. So we have a C++ copy of the object. So kind of example here, but because it's quite difficult to Elaine says, there's no seem idea of n. I didn't tell you what n was, did I? You're absolutely right, but you're making assumptions that about n here, which I didn't tell you. I should. You're absolutely right. I should probably fix that. So in this case, what I can do is, I can, if I have a scalar here, b with something which has already been assigned a value, then I can declare it first private here, and every thread will get a copy of b with an initial value of 23, and then I can go ahead and use it. So I can increment it here and use it, and then finally do with it, and then it goes out of scope at the end of the parallel region. And if I then go and access b again outside the parallel region, it will still have the value 23. And here's just the same example from Fortran. Okay, so far we have shared, private, or first private, and our final option here is reductions. So remember that the reduction produces one of these operations, produces a single value from the associative operations like add, multiply, max, min, logical and, logical or. So in this case, what we'd like is for every thread to get a private copy, and then those to be reduced together at the end of the parallel region to give the final result. So to do this, we can use the reduction clause. So instead of declaring these things as shared or private, they're declared as in the reduction list. And in addition, in this case, in addition to the list of variables, we also need to specify the operator we're going to use to combine them at the end of the parallel region. So the syntax looks like operator, colon, then the list of variables. As well as scalars, it's also possible to have reduction arrays. And the meaning of this is that the reduction is done separately on every element. So every thread gets a copy of the array, and then at the end of the parallel region, every element is of the original gets formed as the sum of the corresponding elements in the private copies. So it doesn't form a sum of the, what you might think it does is that it forms the sum of the whole array into a scalar. It doesn't do that. Okay, it does the reduction element wise. In order to make this work in C and C++, we actually need to use a special OpenMP syntax for array sections. So the reason for that is that usually what we're dealing with here is actually not really an array pointer to some memory, and the C compiler cannot tell how big that thing is in order to make the private copies of it. So you have to use this special syntax to tell it. It's fine in Fortran because Fortran arrays are special objects and in themselves, and they carry around the metadata which says how big each dimension is. But you can also use Fortran's subarray syntax here as well if you only want to operate on part of an array. Okay, so suppose what we want to do is actually form the sum of all the elements in this array C here. And what I could do is I could have a scalar B, which has some initial value. So I know typically in most use cases that initial value would be 0, but it doesn't have to be. So there can already be some existing valid value in B. And what essentially happens here is at the beginning of the parallel region, the value in that original variable B is saved and remembered. And by declaring it in the reduction clause, then each thread gets a private copy of B. And because it's the plus operator here, those copies will be initialized to 0. So the initialization depends on the operator, and the private copies are initialized to the identity element for that operator. So for addition, it would be 0. For multiplication, it would be 1. For min, it would be the largest representable number in that type, and so on. So then all the accesses inside the parallel region refer to those private copies, and you can do what you like to them. There's no restriction. They just behave like regular private variables inside the parallel region. So you don't have to use this operator here does not have to match this one in any way. You can do what you like. And then at the end of the parallel region, what happens is that the values in the private copies are added back in to the original variable. So what I will end up here is in B is the value 10 plus the sum of all the elements in the array. And here's the same example in Fortran as well. Any questions about that? It looks a bit odd when we're dealing with parallel regions. When we come to deal with parallel loops, then the semantics for reductions makes more sense, because it allows you to treat the sort of common use case in a way that doesn't require you to write any code. You can do everything with just the OpenMP directives. It means you can leave the sequential code as it is in the sort of common use case. So then ask, isn't B initialized to 0? So the answer is, question is, well, which B? Okay. The private copies of B are initialized to 0. The original variable B retains the value 10, and that is included in the sum at the end. Good. Okay. So if you're going to do the practical exercises, then the first one up after Hello World is a little simple piece of code. What it does is it computes the area of the Mandelbrot set. And so I'm sure you're all familiar with the famous fractal. So what this code does is it essentially draws a box that contains the set and then puts a grid of points into that box, so a two-dimensional grid of points. And then for every point, it then does a test to see whether that complex value lies inside the set, so it's a black point, or outside the set, so it's a white point in this picture. And then it just takes the ratio of the number of points inside to the total number of points, multiply that by the area of the box, and that's your answer. So this is a nice trivially parallel problem because the test for every point is independent. So you can parallelize that with a parallel region. So I do encourage you to do them in the order that they appear in the sheet. So try doing this with just a parallel region and the runtime library calls first, and then afterwards you can do it with the easier way with the work sharing directives that I'll talk about in the second section. Okay, any other questions? Particularly ask, are reductions deterministic for floats? So that's a very good question. Unfortunately, the answer is no. Okay. According to the OpenMP specification, you cannot rely on repeatability on reductions for floating point operations. Most implementations, however, do support it in the sense that if you do the same, if you run the same code with the same number of threads, then you will get the same floating point result. But it is a quality of implementation issue and not something that's mandated by the specification. Of course, if you use different numbers of threads, then all bets are off. Then you are likely to get different results. So yeah, as you probably expect. Okay, good. So let's give ourselves a break and let's resume on the hour. So at 3 o'clock UK time. Okay, good. So let's move on and start looking at the work sharing directives. Okay, so I've got a question before we start. Great. Okay, how to obtain the value of the environment variable OMP num threads from within my program? Okay. There is some subtlety here in that you can sort of do that. There's an environment variable called OMP get max threads, by a function called OMP get max threads. However, what that does is that will return a value which the number of threads in the next parallel region will exceed. You can't absolutely guarantee that you will get number of threads. The implementation always has some get out to deliver you fewer threads than what you asked for. So if you do crazy stuff and ask for 1 million threads, then the implementation isn't required to deliver you that. And although what that returns will initially be the value in the OMP numThreads environment variable, you can also change that value using a different function. You can use OMP set numThreads, and then if you call OMP get max threads again, that'll reflect the change and won't reflect the original environment variable. So, which is probably what you want, but if you really want to get the value of the environment variable, then you would have to use getenv, or to directly read from the environment. So the rules for controlling number of threads are a little bit complicated. But we'll talk about this later on, because it becomes, say, with one level of parallel region, it's fairly straightforward. Once we come to dealing with nested parallel regions, then it's much more important to be able to control the number of threads that different parallel regions are going to use, and we'll talk about later on in the course. Okay, so work sharing directives. So these are directives that appear inside a parallel region, and they indicate how work should be shared out between the threads. So instead of the default behavior where all the code inside the parallel region is executed by all the threads, work sharing directives, if you like, override that default and do a different sharing. So first of all, look at loops, and probably this is the most important, or at least the most widely used feature in OpenMP, is to parallelize loops. And that's simply because loops are the most common source of parallelism in most codes, so particularly in numeric and scientific programming. So parallel loop directives are really important, a very important feature of OpenMP. So, I wouldn't mind guessing that if you did a survey of all the OpenMP code in the world and counted up the directives, then the vast majority would be parallel loop directives. So a parallel do or for loop divides the iterations of the loop between the threads, instead of every thread executing the whole loop. So this loop directive appears inside a parallel region, and it indicates that that work should be read out instead of replicated. There's also a synchronization point at the end of the loop. So all threads must finish their set of iterations from the loop before any thread can proceed executing the code after the loop. That's the default behavior. There's a way to change that, which I'll talk about later on. So the syntax looks like this. It's, for Fortran, it's !OMP do, immediately followed by, let me get my pointer, !OMP do, immediately followed by the do loop. And in most cases, and the exception I'll also cover later, the end, you can put an end do directive. It's not compulsory. The compiler is able to figure out on its own where the loop ends. But some people like to include it so that everything's symmetric in Fortran. So every OpenMP directive has a matching end. So That's just a matter of taste, really. C and C++ is hash pragma OMP4, immediately followed by the for loop. And the important thing to note here is that you cannot have curly braces enclosing the for loop. Okay, so the next statement, the next piece of syntax immediately after the for directive must be the for loop itself, and you can't enclose the for loop in curly braces. So good question. Can we use these with C++ stuff? This works for, let me get this right. This works for C++ random access iterators. Okay, so Melinda asks, to know at the end of some directive regions like for and single, there's an implicit barrier. Where can I find the full list of those? Oh, that's a really good question. So I suspect there isn't, even in the specification, there isn't actually a list of those all in one place. Well, there might be. I'd need to check. I'll have a look in this. I'll have a look in the specification for you. But essentially, it's 4 single sections work there in Fortran. I think that's it. Nicholas asks, general question, does Python support OpenMP in a similar way? No, it doesn't, unfortunately. Okay. So, yeah, I'm afraid Python does not have an equivalent. So Python has a threading interface, but in sort of the most popular Python interpreters, that doesn't actually allow you to do useful parallel programming because it only allows one thread to execute at a time. So generally speaking, Python threads is not a useful portable way of doing parallel programming, somewhat sadly. Okay, so I think there is, so one of the Python extensions or derivatives does support something which does parallel loops. I think it's Python. Yeah. So there are packages where you get some workarounds. That's true. I think Python has parallel loops, which essentially map down onto OpenMP parallel loops, but the functionality is very limited from what I can remember. So it has some capability for parallel loops, but it's nowhere near as extensive as the whole MP. Okay, so there are some restrictions with what you can do in C and C++ with parallel loops, because the for loop in C is the general while loop, and in order for parallel loops to work in OpenMP, they have to have this property where the number of iterations or the trip count can be computed before the loop starts executing. So it essentially has this sort of classical pattern, which looks like, for some variable equals something, variable less than or equal to, greater than or equal to something else, and then a constant increment expression. So, the most common type of for loops that you write, sort of for I equals 0, I less than n, I plus plus, matches this pattern. And also, you're not allowed to modify the loop iterator variable inside the body if it's a parallel loop. Okay. So, sort of canonical example. So, and again, I think I've got my indexing messed up in C here, but okay, if you can forgive me that. Then here's the loop, okay, and it has independent iterations. So every computation of BI here is independent from every other one. We can do them in any order we like. So that's a safe loop to parallelize. Then we need to be inside a parallel region. So here's my parallel region, #OMP parallel 4, and the outer set of curly braces. And then I put this for directive immediately in front of the for loop, which tells OpenMP to divide these iterations across threads and not execute the whole loop in every thread. Okay. So same in Fortran. So here's the loop. Then have to be inside a parallel region in order to get more than one thread, and then apply the do. And in this case, I have used the end do directive. Yes, Melena asks, it's important to have two directives, and when we could go for parallel 4 instead. Right, I'm just about to cover that. Okay, yeah. So yeah, I'll if I haven't answered your question in a minute, then get back to me. No, not at all, not a problem. Don't worry. Okay, yeah. So this pattern is so common. Okay, so if you just want to parallelize a single loop or a single loop nest, then this pattern of having a parallel region with a do or for directive inside it is so common that OpenMP provides you with this shorthand version. Okay? So in Fortran, you can combine a parallel region and a work sharing directive with OMP parallel do, immediately followed by the do loop. And in C or C++, #pragma OMP parallel 4, immediately followed by the for loop. So instead of what I had on previous slide where they're separate, then you can do the compact version like this. Okay, and those two things are exactly equivalent. So the work sharing directive, you can also have private, first private, and reduction clauses that would refer to the scope of the loop. Private and first private are unusual because that would mean you had a variable that was shared inside the parallel region, and then you wanted a private copy just for the extent of the loop. So that's a fairly unusual use case. Reduction, however, is useful. So it can be situations where you have a loop that does a reduction and you actually want the result of the reduction to be available in the code inside the parallel region after the loop. So you couldn't have the reduction on the reduction clause on the parallel region because that meant that the sum or maximum or whatever it was wouldn't be computed until the end of the parallel region. So having a reduction clause on the work sharing directive is useful, because then the result is computed at the end of the loop and not at the end of the parallel region. So the parallel loop index variable is always private by default, and other loop indices are always private by default in Fortran, but not in C. So in C, C++, you have to declare them. You usually declare them inside the scope of the loop anyway, or if you don't, then you have to declare them private. Otherwise, say the combined directive can take any of the other clauses available for the parallel region. So this is convenient. This shortened form is convenient, but it's important just not to get them mixed up. Okay, so the combined directive is not the same, does not have the same meaning as the work sharing directive on its own, and it doesn't have the same meaning as a parallel region on its own. So just if you have nested directives, just make sure that you are clear about what you really mean and which ones you need. Otherwise, you can get yourself into a bit of a mess where you're writing something that's syntactically, because nested parallel regions are allowed, you can get yourself into a situation where you've written something that's syntactically meaningful, but doesn't do what you want or expect. Any more questions for now? Can you nest OMP4s? No, you can't. Okay, so I will talk later on about how we deal with nested loops, but you cannot have a for construct inside another for construct. That's not allowed. If you'd like to think about one way of thinking about that is it's not allowed because the for construct does not create threads. So you can nest parallel fors, and I'll talk about parallel regions and dealing with nested loops later on in the course. Good. So if we don't specify any additional clauses, so you do SIMD instead of nested for. Yep, you can do. I'm not really going to talk about SIMD in this course, but yes, you can have. You can nest SIMD loops inside for loops, and you can have both for and SIMD on the same loop as well. Yeah. So, but again, those are different. Okay? So SIMD is for vectorization, and whereas for is distribution across multiple threads. So in some sense, they are complementary and operating at different levels of parallelism in the hardware. Okay, if we don't specify anything else, then the loop directive will just try to partition the iterations as equally as possible between the threads. However, there is some ambiguity there in the sense that the specification doesn't say how the runtime should deal with any remainder here, or the compiler or the runtime should deal with the remainder. So things don't divide nicely. You don't actually know precisely what's going to happen. So if I had a loop with 7 iterations and 3 threads, I might get it partitioned as 3 and 3 and 1, or I might get it partitioned as 3 and 2 and 2. And I don't know which I can't rely on. I can't rely on any particular distribution of the remainder iterations to threads. In practice, I think most implementations will actually do this, because it makes the remainder computations a bit easier than trying to split them across threads as evenly as possible. You find most implementations just tend to leave the last threads with fewer iterations. Okay, so that's fine as long as each iteration is going to take more or less the same time to execute. But that's quite often not the case. And so if we have unbalanced workload in the loops, then we can use the schedule clause. And that gives us a variety of options for specifying which loop iterations are executed by which thread. So this is a clause which appears on the end of the do or for directive, and it looks like schedule, then in brackets a kind, and possibly also a chunk size. So the kind can have one of these values: static, dynamic, guided, auto, and runtime. So I'll talk through what each of those means in a minute. And where the chunk size is used, it has to be an integer expression with some positive value. And it doesn't have to be, so like this. Okay, so this would be a valid Fortran example: schedule dynamic, 4. This does not have to be a compile time constant. It can be a runtime variable expression. So, for example, if I define a variable in between pragma parallel and pragma for, and I write it in the loop, is it shared or private? Yeah, no problem. It's still private, is the answer. Okay. You cannot have a variable that's already been privatized in an outer scope and then make it shared again. And there are other rules like that as well. So, for example, a variable that's a reduction on a for directive has to be shared in the enclosing parallel region. Otherwise, it's not clear which. If it were private, it would be unclear which private copy was being used as the original variable in the reduction. So reasoning about, so when you get into nested parallelism, then reasoning about shared and private variables can get a bit hairy. So one way that helps think about this perhaps is that if it's shared, then it refers to the existing storage with that name. If it's private, then I'm making a new copy. Okay, so for static schedule, so if I have static schedule and no chunk size, that's the same as the default behavior. So with no chunk size specified, iteration space just gets divided into approximately equal chunks, and one chunk is assigned to each thread, and that is done in order. Okay, so the logically first group of iterations always goes to thread 0, and the logically last group of iterations always goes to the last thread. If we do specify chunk size for static, then the iteration is divided up into what's called chunks. Okay, each of that number of iterations, and those chunks are assigned cyclically to each thread in order. So this is a block cyclic schedule. So okay, maybe easier to see with a picture. So suppose I have a loop with 46 iterations in it, and I have 4 threads, so threads 0 to 3. So then if I specify schedule static, that would do an equal division as possible. So threads 0, 1, and 2 would get, do my sums right, good 12 iterations each, and then thread 3 gets the remaining 10. I specify a chunk size, so suppose I specify a chunk size of 4, then I divide the loop iterations up into blocks of 4, into chunks of 4. So thread 0 gets the first 4, thread 1 the next 4, and so on, and then we cycle round 0, 1, 2, 3, 0, 1, 2, 3. So each of these chunks has 4 iterations, except possibly the last one, if it doesn't divide nicely. So next is dynamic. So this also divides up the iteration space into these fixed size chunks, but instead of a cyclic distribution, it assigns them to threads on a first come, first served basis. So in other words, whenever a thread finishes a chunk, it gets assigned the next chunk in the list. And in this case, if we don't specify a chunk size, it defaults to 1. I'll come to an illustration of that in a minute, but also want to compare that with guided. So guided schedule is similar to dynamic. Instead of having all the chunks the same size, they start off large and get smaller in a well-defined exponential fashion. So the rule is that the size of the next chunk is proportional to the number of remaining iterations that haven't been assigned to threads yet, divided by the number of threads. Okay. So there's still some implementation dependent detail there, which is the constant of proportionality. But as far as I'm aware, all implementations use a half. So the algorithm is how many remaining iterations are there? Divide that by the number of threads, divide that by 2 again, and that's the size of the chunk that will be assigned to that thread. So in this case, the chunk size doesn't do very much. It just specifies a minimum size of the chunks. And again, that defaults to 1. So back to my example with 46 iterations again. If I specify dynamic with a chunk size of 3, then I get iterations assigned in chunks of 3. So thread 0 gets the first 3, thread 1 the next 3, thread 2 the next 3, thread 3 the next 3. And then whichever thread finished its first chunk first, so in this case it's thread 1, the black thread, it gets the next one. And then suppose the grey thread finishes next, it will get the next one in sequence. And that might mean, for example, in some cases, then a thread gets to execute more than one chunk in sequence, so on. Guys, the same idea, this first come first served method, but instead of all the chunks being the same size, they start off large and then they gradually get smaller and smaller until they get down to this. The chunk size is the minimum size here. So in this case, all the 3 say is don't make any of these chunks smaller than 3. Again, possibly with the exception of the last one, if the division doesn't work out exactly. Next option is auto, and that essentially says, okay, I'm just handing over all the control for this to the OpenMP implementation. So it essentially lets the runtime have full freedom to choose its own assignment of iterations to threads, and that doesn't have to be one of the other algorithms. It can be anything it likes. And it also allows the implementation to implement other algorithms, including ones that might try to have some learning behavior. And the final option is runtime. So all this does is it allows you to set the schedule with an environment variable. So this is an environment variable called OMP_schedule. So in the code, I can say schedule runtime, and then before I run the code, can set the environment variable, say, to dynamic 1, and that means that all loops in the code will have schedule runtime specified. This particular run will use dynamic 1. So this is just a convenience for experimenting with schedules and chunk sizes without you having to recompile the code every time. But it's probably best not to leave this in production code. Okay, so it's good for tuning experiments, but then once you've found a good solution, you should probably encode that rather than rely on anybody who's using the code to set this correctly. That's a very good question. Which schedules are more prone to false sharing when the array element is smaller than the cache line size? Okay, so yeah, so assuming you have consecutive array elements indexed by parallel loop variable, then you have a potential problem with false sharing, which I will, for anyone who doesn't know what that is, I will discuss that in the last lecture of the course. So essentially, which schedules are prone to that? So that would be static with a small chunk size, and dynamic with a small chunk size are probably the most likely ones to encounter false sharing problems. But it does, of course, depend on how the loop index is used to index into the arrays. Okay, so we've got some holding amount of choice here. So if your loops are well balanced, then static is probably the best. Okay, there are exceptions. I will mention exception in the performance lecture later. And static with a chunk size tends to be a good solution where loops have relatively mild and smooth load imbalance. Okay. What do I mean by smooth? That means if neighboring iterations tend to have similar loads, then static with a chunk size can be a good solution. Dynamic is useful if the iterations have widely varying loads. So if you have iterations where some iterations are, say 100 or 1,000 times more expensive in terms of execution time than others, then you might want to use dynamic. Say again that if the loop is indexing into array type data structures, or any kind of data structure, then the problem with dynamic is that it tends to ruin any data locality, because essentially you have no idea which thread is going to access which data, and if you run the same loop twice, then you'll probably get a different mapping. So small timing differences in dynamic will often mean that you get a very different assignment of iterations to threads, even if you execute the same loop, exactly the same loop twice. Guided is a bit of a compromise, so it's less expensive than dynamic in terms of its overheads. So the problem with dynamic is that it requires some sync, and guided is that doing first come first serve requires some synchronization between the threads so that they agree on who gets the next chunk. Otherwise, there could be potentially an internal race condition for that. So, and that synchronization costs something. So guided has lower overheads in terms of the internal synchronization, but it might not balance the load as well. So, for example, if you have a loop where the first iterations are the most expensive, they will get all put together in one of these big chunks at the beginning, and all assigned to the same thread, and that might not balance the load very well. And then also, is essentially a mechanism for allowing the compiler to implement its own options here, and the compiler documentation may or may not tell you what it's trying to do. Okay, so any questions about loop schedules from you on? Okay, good. So next one is single directive. And so this indicates that a block of code is to be executed by a single thread only. So what happens? So we're inside a parallel region, and there's a piece of code where we only want one thread to execute it and not all of them. So that's the case you're thinking of here. What happens is that the first thread to reach the single directive will execute the block of code, and then there's synchronization points, another one of these implicit barriers at the end of the block. So all the other threads wait until the block has been executed. No particular surprises with the syntax. So for Fortran, single end single with a block of code, and same usual thing for C, C++, OMP single followed by the structured block. So here's a simplified looking use case. So suppose I have a parallel region, and I have a couple of data structures called X and Y. So maybe you can think of these as pointers to some data structures. So I want every, and they're going to be shared. So I want to essentially have every thread call some setup with and pass it X, and that's going to internally divide up some work. I don't really mind how. Not really bothered about how. Then I want to read some values from a file into the other data structure Y, and then finally I'm going to do some work on every thread that involves X and Y. So if I only want one thread to do the file I/O, and that's typically best, it's often just confusing and doesn't improve performance if you try to do multi-threaded I/O. And then I can enclose the input inside a single construct. So what that means is that so inside the parallel region, all the threads will execute setup. The first one that happens to finish will go into this block here and execute input. The other ones, in the meantime, may finish setup and they will be waiting at this implicit barrier, implicit synchronization point at the end of the single. Once input is finished and all the other threads reach this point as well, then they can all carry on and execute work. So what's the most often used of single? Yeah, it could be writing to a file, something like that. What else? So yeah, there are other use cases as well. So you can be in the situation where you want to, say you want some, you have say several loops, one after the other, with a bit of sequential code in between them. And for performance reasons, you don't want a separate parallel region. So it helps avoid the expense of closing the parallel region and then starting a new one again. And also, you may be in this situation where you have some piece of work that doesn't necessarily take the same amount of time. So you really want the first thread that finishes to do the sequential thing. So there are a bunch of possible reasons for doing this. You also might want to. You can also use it to synchronize if you want just to write value into a shared variable inside a parallel region. Then you might want to use this, because it means that otherwise you would, if you have every thread writing a shared variable, that's technically a race condition, and also may have some bad performance consequences. So it's better to have one thread to write it, and then you have the synchronization to make sure it's safe for all the other threads to read it. Yeah, so there is a number of different possible use cases for this. Okay, so I already answered Alessandra's question. Yeah, so single works for this basically. So uncommon, but you can also have private variables on singles. Can you have two single directives at the same time? Yeah, potentially yes, but only if you get rid of the synchronization at the end. Okay? The synchronization means that you can't be in, if the barrier means that you can't be in two singles have two singles executing concurrently. But there's a way to get rid of the barrier, and in which case that can happen. Is that right? Yes, I think so. Yes, because you can't have single and separate branches because of the barrier. So as with it's kind of implicitly assumed up to this point, but the structured blocks must really be structured blocks in the sense that you can't branch. What that means is you can't branch into or out of it. Okay, so that's true about parallel regions and most other blocks of code associated with OpenMP directives. Control flow has to go in at the top and out at the bottom. Okay, so I've already mentioned about getting rid of the barrier, this implicit barrier. So the way you do that is with the no wait clause. So you can get rid of the barrier at the end of the loop directive or at the end of single by adding a no wait clause. Of course, it's potentially dangerous, so use it carefully because it's easy to introduce race conditions like this. So in Fortran, this is the case where you need to use the end do because the no wait clause goes on the end do directive, and that suppresses the barrier. And in C or C++, it just goes on the for. So hash pragma OMP for no wait removes the implicit barrier at the end of the loop. And then lastly is master directive. So this is sort of similar to single, but different in a weird and not particularly well thought out way, I think. Anyway, what it does is that instead of the first thread to reach the block of code for master, it's thread 0 that will execute it, and all the other threads ignore it. And as I said, there's this weird asymmetry that for master, there is no synchronization at the end of the block. So other threads just skip over it and keep executing. And the syntax is exactly what you expect. So this is really just syntactically equivalent to a piece of code that said, if OMP get thread num equals 0, do this. Okay, that's all that master really is. Okay, good. Does anybody have any more questions? Okay, so Milena, back to single. Okay, let me find the example. Okay, it's in a parallel region. Does single inherit the variables? Yes. Okay, so if you don't specify these private or first private or reduction clauses on work sharing directives, then the data scoping is inherited from the enclosed parallel region. So if it's private in the parallel region, it'll also be private in the single. So you do have the facility to change. The only thing you can change for single is if you have a shared variable in the parallel region, you can make a private copy or a first private copy for the scope of the single. But otherwise, everything just has everything inherits its shared or private properties from the enclosing parallel region. Okay, so for a private variable, what does it do at the end of the parallel region? It disappears and goes out of scope. Okay, so private variables go out of scope and vanish at the end of parallel regions. There is a way to have thread private data that does persist between parallel regions. I will talk about that later, but it only works in limited circumstances, let me say for now. Yep, that's thread private. Yeah. Yeah. So Alexandra asks, I guess in the single region, you cannot assume you have data from the setup of other workers. That's correct. There's no synchronization, as I've written it here, so there is no synchronization between the threads on entry to the single, only on exit. Okay, so the synchronization point is here and not here. So when input starts executing, I have no idea what progress the other threads may have made. Okay. Yes, you know that this thread, whichever thread executes single, it has necessarily completed setup, but the other threads may not have done. And it's the same with parallel loops as well. There's no synchronization on entry. So when you go into if you're inside a parallel region, when the thread enters a work sharing loop, then again there's no synchronization. You don't know where the other threads might be executing at that point. Can I explain what the difference between thread private and private is? Okay, I have not covered thread private yet, and I will come back to that later. So, but just to give you a sense of what thread private is, it's essentially a mechanism for having private copies of global variables that persist for the lifetime of the program. Okay, anything else? Oh, no problem, Milena. You're very welcome. It's really good. So many good questions today. It's really nice to see. Okay, very good. So if you're having any problems, so see a few people have already registered for machine accounts on Cirrus. If you're having any problems, if you have any questions about practical exercises, then say please either post on the chat page, or you're very welcome to send me email as well. I'm very happy to answer questions by email. So yeah, any problems, please let us know. And hope you have some fun doing some programming. Otherwise, so back again same time next Tuesday. Look forward to talking to you all then.